MC this seminar is Associate Professor Abdolhamid Alizadeh. So he got his PhD from Sina University in Iran and the University of Western Ontario in Canada in 2005. And after that, he is becoming a research fellow in the University of Western Ontario, Canada until 2005. He was a visiting professor in the same university in 2007. And he was an assistant professor at the chemistry department at University from 2005 to 2010. He has also director in the nano-chemistry department at University in 2012 and until 2013. And he is an associate professor in the chemistry department at University. And at present, he is with us in Ibnu Sina Institute as the postdoctoral fellows at the Universiti Teknologi Malaysia. So, Associate Professor Dr. Abdolhamid Alizadeh also already got many honors and awards, such as in the Brazil University, he got the Premier Research Excellence Award in 2007, 2008, and also in 2012. So he has been also organized many symposiums and has been also active members in some professional memberships. Actually, he is already have more than 29 graduated students, and currently he has 9 students working on the material chemistry and clean organic chemistry. His specialization techniques include in the synthesis, characterization, and study of the modified metal nanoparticles, and then synthesis application of modified ferromagnetic nanoparticles in organic chemistry and nanomedicines, synthesis, characterization, and application of organic and inorganic hybrid nanomaterials, electro-organic synthesis of organic compounds, synthetic organic chemistry, ionic liquid chemistry, and several material characterization techniques. So if I have to read all of the career, it will be taking a long time for us to hear. So I believe that all of you already want to hear the talk today is bridging between organic chemistry and nanochemistry. So let's welcome Associate Professor Dr. Abdolhamid Alizadeh.
Good afternoon. Thanks for listening to me, Dr. Lee. And I would like to take this opportunity to appreciate all of you being here at this time. And especially I would like to thank Professor Dr. Mustafa Shamsuddin having me here as a postdoctoral fellow and giving me this opportunity, presenting my a brief of my research during, let's say, 10 to 12 years. So, bridging between chemistry and nanochemistry needs a chemist and a materialist. So, what was the main target during this research, 10 years, 12 years, was taking benefit and advantages of chemistry in favor of nanotechnology, making some nanomaterials, nanocomposites, and then taking advantage of those nano-engineered materials in chemistry as catalysts, as sensor, as nanocarriers, and so on. So, first, we go to the first part to explain how can chemists help nanotechnology. And at the end, or continuously, we will talk about how a composite made from chemistry and material chemistry or nanotechnology can give help to chemistry, especially organic chemistry or analytical chemistry or something like that. Mainly, I'll talk about nanosensors and nanocatalysts, basically heterogenized nanocatalysts on solid materials. So, before doing anything, we need to know where are we going. Talking about nanotechnology, you know, everywhere we hear this in media, in news, you know, internet, everywhere, in too many meetings, we hear about nanotechnology. As you see, basic advancement in science and technology come twice a century. Starting from textile, railroad, automobile, computer, and now nanotechnology. Each one has three main parts. Introduction of technology, which is discovery, widespread adoption, takes longer time, and then maybe end of rapid growth phase and stable position. So, if you look at the nanotechnology, we have started, let's say, from 1997, and still we are in introduction of this technology. So, as a chemist, we are a part of this, let's say, multidisciplinary area, which is nanotechnology. Has something from chemistry, physics, biology, engineering. So, we are going to talk about the materials which they are in nanoscale. When we say nanoscale, this is the correct definition. One of any material, if you want to consider it as a nanomaterial, one of its dimensions should be between 1 to 100 nanometer. A nanometer, 10 to minus 9. Imagine the scale. So, actually, if you got any question, please just remember the place. I'll talk about something in Iran, then I move to Canada, then I move to Iran, then to Malaysia. If you just give me the place in your question, then we will go on and we can talk about it. I was a postgraduate student during this year, 2001-2004, and I was working on green chemistry, electro-organic synthesis of materials with potential applications, especially in biological applications. We were able to, actually I am still working in this area, I have some students working in this area. We were able to start with a very simple and green condition, water, room temperature, room pressure as a solvent and condition, adding some starting material, let's say electroactive material here, and too many nucleophiles. And then simple chemical reactions, mostly CC coupling, CS coupling, CN coupling, and so on. So we were able to make a library of too many bioactive molecules. Then I got an opportunity to join to a group of Professor Mark Workentin, who was a material chemist in University of Western Ontario in London, Ontario, in 2004. So I was a pure chemist and knew nothing about nanotechnology and nanomaterial. So I started to learn from his senior students in lab. So I got interested in nanoparticles. And we were inspired with this very beautiful paragraph where nature finished producing its own species. man begins using natural things and with the help of his nature to create an infinity of materials. Leonardo da Vinci. So, we started bridging between chemistry and nanomaterial chemistry. So also we had our special flag between Iran and Canada, and there was a label on top of the main entrance in lab. It was Iranada, combination of Iran and Canada. So we started, and the first thing I was interested was removing substrate from gold surface or adding functionality to the substrate. For example, here, let's say these are simple chemical reactions, quite simple reactions. Everyone knows about them. For example, here, we were interested to see, can we have a molecule attached to the surface of gold nanoparticle, and then, wherever we want, doing something here and release them in solution. The main target was drug delivery. Or how can we put a molecule, a biomolecule, an enzyme, a protein, and blah 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 at the surface of nanomaterials, especially noble gold nanoparticle, biocompatible materials. So, just imagine if a nanoparticle was the size of a football, then a virus should be as big as a person, and a red blood cell would be the size of a rugby field, and a donut would be as big as New Zealand, a country, and a kiwi, which is very famous in New Zealand, would be as big as the world. So we started the chemistry and investigation of physico-chemical aspects of these nanomaterials, especially nanoparticles, gold nanoparticles, modified with simple organic molecules based on the chemistry of sulfur and gold, which they usually make covalent bond. As I mentioned earlier, we were interested to see, can we strip away the molecules from the surface one by one, or control release? So we took this, and in the presence of a radical source, which is quinacolone, everyone knows about the photochemistry of this molecule. If you irradiate that, you will get immediately two free radicals. And what we saw was reaction of these radicals with this molecule at the surface and removing them into the solution. So, starting from simply monitored by, let's say, proton NMR. Before irradiation, you will see methyl group signals here, and CH2, 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 CH2 groups here. That's it. The story about the broadening of these signals is also too long. I'm not going to explain that, why these are wide signals. But when you start to irradiate them, you will get these molecules freely released into the solution. This means you can put anything you want, and you can release anything you want into the solution. But the problem was irradiation source. This is UV irradiation, so you can apply it to biosystem. Anyway, so we started with this size of a nanoparticle, which is 1.6 nanometer, very small, synthesized through two-phase procedure, which is also called David Schifrin's method or Matthias Grass method, compared to the one-phase synthesis, which is citrate synthesis.
So we started with this. We asked ourselves, what happened to the core after removing the organic molecules from the surface? So we followed this over the time. After 90-minute irradiation, we saw this absorption, and after 210 minutes, we got this. And I'm 100% sure that you know about the surface plasmon of metallic nanoparticle, especially gold, which is around 520 nanometer. So this means when you have nanoparticles smaller than 5 nanometers, let's say 2 nanometers, 3 nanometers, there is no surface plasmon bond. But when they are bigger, you can see surface plasmon absorption. So we figured out these are getting together after stripping away the ligands. So we proved this claim with the help of high resolution TEM, starting here, middle, and at the end, in the sides. So, and also color change immediately after easily visible color change, starting from, let's say, red to purple to blue, depends on the time of irradiation and depends on the size of final nanoparticle. Anyway, this was our suggested mechanism. We here, if you focus here, we started with these small nanoparticles. We tried to release these molecules from the surface. As a result, they combine and they attach together and they make bigger and bigger. And also, we were able to calculate the stoichiometry of gold and organic component with the help of NMR and TGA and many other characterization techniques. So, based on this finding, we were also interested. To put some label here, fluorophore, and radical source at the end of the surface, not adding quinocolone as an external radical source. So we irradiate this, and while it has some, let's say, fluorophore, photoactive, bioactive, and electroactive moiety at the end, so then we can easily see before irradiation, no fluorescence. After irradiation, you will see fluorescence, because when they are attached to the surface, it's quenched. Even you can also follow, monitor. This is a kind of TLC, monitoring the reaction progress with photoactive, fluoroactive, or electroactive molecules. So, having these all, here, next one, here. Having these all together, we also try to investigate this chemistry at the surface of two-dimensional gold, let's say gold electrode, which is self-assembled monolayer technique. So we made self-assembled monolayer technique and we did the same chemistry and we saw same release. Also, we were able to play with the tail group all attached to the surface of gold electrode and do some organic reaction. Here, you can oxidize hydroquinone terminal group to this quinone, and then you have glutathione here. You can easily attach it through Michael addition reaction. Even you can measure the loading amount with the help of electrochemical techniques. And my best and favorite part of this research field was making sensors, naked eye colorimetric sensors for metal ions. We started to put some simple complexation chemistry concepts. Complexation of chronometers with metal ions. Complexation of organic ligands with metal ions, let's say organometallic chemistry. So we started with this monoazide chronometer at the end of this nanoparticle, and we used it as a lead colorimetric sensor. Also, we tried to play with the other donor ligands and put them covalently at the surface of gold and introduce new colorimetric sensor for copper, silver, and mercury also. If you look at the end, you know, the scaffold is same, but you can play as a chemist with the organic tail group, then you can introduce new application. I'm going to explain one of them. How can we do this? We need this molecule attached to this long alkyl chain with SH at the end. So we are organic chemists. We can do synthesis. So we started this monoazide chronometer, and through this simple one-by-one organic reaction, we can make this molecule. If you have this SH group here, you can simply imagine this nanoparticle without this chronometer. That's the starting nanoparticle. You can take that, and with the excess amount of your incoming ligand, which is this, you can do place exchange reaction. You will see there is a combination of these ligands and new ligand. You can easily prove this with the help of proton NMR and other techniques. So the chemistry was synthesized of this, synthesized a simple nanoparticle, and make this combined one or modified nanoparticle and add to the solution of lead. There is a chemistry behind chronometer and lead. They can easily make 2+1 complexation, 2+1. So we started with nanoparticle, and we got this observation which also says the size is below 2 nanometer, 3 nanometer, also with the help of T, and you can see this. But when we add cation, metal ion, you see new surface plasmon bond here. This means nanoparticles are getting bigger. This is the clue for agglomeration, aggregation. Why? Because one chronometer comes from this nanoparticle and another one comes from here, and with the help of one metal ion, they get together. Aggregation. This is colorimetric sensor based on aggregation of gold nanoparticles. This is the schematic illustration, and before and after, the color is changed. So, also it was selective. It has no response for silver ion and also for mercury. Nothing changed. So it was simple, selective sensor. Also, as I mentioned earlier, we played with the tail group and we made this 3D dicarboxylic acid. I forgot the name of this molecule. And it was also colorimetric sensor to detect copper, CO2 cation. Also, it was selective over the cobalt, zinc, lithium, and lead. So, optical, or let's say colorimetric sensor, work based on the surface plasmon bond of gold nanoparticle. Then, I went back to Razi University and I joined to the Department of Chemistry and start to study heterogenization of homogeneous catalysts with the help of solid scaffolds, solid supports. So we got interested in silica chemistry because of low cost and also stability, and also surface hydroxyl group that lets you to modify and put too many molecules or alkyl chain at the surface. And of course, you know, there are too many different mechanisms to heterogenize, to immobilize a molecule to a surface through hydrogen bonding, electrostatic interaction, covalent bond, and so these are some examples. Let's say here, electrostatic interaction. And we were interested to study a family of organic molecules called organosuperbase attached to the surface of silica or nanocomposites. People have made too many modified silica surface with the help of amine and different molecules, but we got interested in metformin chemistry, which is a biguanic structure, and it is organosuperbase. If you look at pKa, then you'll find how a strong base these molecules are, organic base. Because as I mentioned, we take advantage of organic chemistry to synthesize nanocomposites, and then we need them in organic chemistry lab as a catalyst. So we put organosuperbase at the surface. We ask also, can we use this molecule while it is immobilized at the surface as a catalyst? So we plan to synthesize silica nanoparticles with metformin, or let's say biguanine, attached to the surface, and also SPA15 mesoporous structure of well-ordered silica materials inside the channels. So we started this chemistry, and of course it was characterized with the help of too many techniques. When we are talking about the porosity, mesoporous, we have to be careful about the size. MCM41 is silica material. SPA15 is also silica material, but different channel size. So we characterize the matter. I'm not going to explain one by one. We just make sure that it is mesoporous and has surface area, total pore volume, mean pore diameter, and everything was checked. Then and also the structure with the help of SEM and TEM was studied. If you look at here, this is well-ordered SPA15 channel capsule-like structure. So we took those nano-engineered materials back to the organic lab and asked other students, which they are still pure organic chemists, to use our catalyst as a catalyst in simple organic chemistry, let's say CC coupling, Henry reaction, and also CC coupling reaction. If you look at here, the catalyst, metformin on the surface of silica was, in this case, although reaction was completely chemoselective, or even in the case of Henry reaction, no nitroastyrene, no nitroalkene compounds, only Henry product, and here only aldol product. Chemoselectivity was considerable, and also in this reaction, very high yield. And the main point is you can get your catalyst easily back with centrifuge or ultra-centrifuge technique. So the only problem, I'll go and explain the problem with these materials later, but also we were interested to make the complex of palladium with metformin at the surface of silica and use it again in organic chemistry lab as Suzuki coupling reaction, as a catalyst for Suzuki coupling reaction. So we made this, and of course, we have to characterize the structure. This is just to show the size of capsule-like SPA15 materials. And it was used, the palladium complex one was used in Suzuki coupling reaction, considerable yield, excellent yield, and also oxidation of alcohol, benzyl alcohol to benzaldehydes. So, one interesting point we figured out was after catalytic reaction, let's say 1, 2, 3, 4 times, we saw black spots attached to the surface of SPA15. You can see everywhere. So that was palladium nanoparticles, because the solvent usually had some, actually here, maybe I'm wrong with this, I can't remember, maybe it should be ethanol. I can't remember, but when we saw these nanoparticles form at the reused catalyst, so we thought of reaction mechanism. We actually proposed this mechanism starting with this complex. Let's say this is attached to the surface, and with alkyl halide, you can get, with the help of potassium carbonate, you can get this intermediate and coupling product. But why catalyst is still active after seeing palladium nanoparticles at the surface? Because there is a cycle. You see palladium 0 nanoparticles in air, they can get oxidized, and also we have some metformin at the surface, and with the help of base, partial oxidation of palladium 0 to palladium 2, again compensation, and this cycle. So based on this finding, we also played with other ligands. Phenanthroline, we know that is very good ligand for too many metal ions, especially for iron. We also studied palladium complexation with this phenanthroline at the surface of SPA15, and also complexation of copper with this moiety at the surface of silica, and each one was used as Suzuki Miura coupling reaction catalyst and aerobic oxidation of alcohol catalyst, and in the case of copper, we used it for Ullmann reaction coupling, Ullmann coupling, and click chemistry. Look at the yields, almost high and excellent. So, final application was bioapplication. I'm not go on details, but simply when you have metformin attached to the surface, as I mentioned earlier, it is organosuperbase. If you take a medicine with acidic property, then you can simply see proton transfer between them. For example, this is ciprofloxacin. If you take ciprofloxacin, you will immediately you'll see this proton transfer here and electrostatic interaction between anion of medicine and protonated metformin at the surface. So we also applied MIP technique to have controlled release. In MIP technique, you use polymer to cover the drug or medicine which is attached to the surface in special pH, and in another pH you can easily remove the polymer and control release. This also, research paper is still on progress. Please just have a look here. Metformin at the surface of silica or SPA15. In pH, at pH 7, has no release percentage. Because me, I've studied other medicine, metformin, amantadine with the other acidic or basic modified surfaces, dopamine and blah blah blah. But the interesting thing, we saw no release in pH 7 and release in acidic and basic pH. So, organic chemistry, simple organic reaction is the fundamental for these studies. You have to be able to put metformin at the surface and prove it and study structure, then you can use it as a catalyst, as a nanocarrier, and too many other applications. So he bring organic, inorganic engineered nanomaterials were used as reusable catalyst and also nanocarrier. We just thought, okay, can we also think of easy separation of these materials? So we put magnetite inside the nanoparticle for easy recovery at the end of reaction. We did almost same chemistry, metformin at the surface of silica, but having some magnetite Fe3O4 core inside the system. As you see here, these are Fe3O4 magnetite, and this is silica layer as a core shell system. Of course, magnetism and simple catalytic application in organic chemistry reaction. And at the end, you can see easily less than 15 seconds, you can apply an external magnet, get your catalyst back and wash it and use it. Okay. So, also the same chemistry was followed with the palladium complexation at the surface for Suzuki coupling. And same thing, at the end, we saw palladium nanoparticles form at the surface and everywhere. Even with the help of EDX, we were able to see palladium at the nanocomposite, present in the nanocomposite. So, also we were interested to use other coating layer instead of silica in the case of magnetite nanoparticles. Because silica is used for two main reasons. First, protect the core of more oxidation. And the second one is to give you better surface to modify with the help of OH group and so on. So we thought, what about making it more biocompatible? If you take dopamine, you can easily stabilize these nanoparticles and keep them stable in solution. So we made this, and with the help of this spacer, again we put metformin excess amount at the surface. If you look at here, loading percentage of metformin is too much. We can call it polydentated or polydendron-like modified core shell system. And also, of course, complexation of this palladium, this metformin with palladium was studied, and we use all of these in simple organic reactions as recoverable catalysts. And as I mentioned earlier, there are two main ways to produce or to synthesize metal nanoparticles, especially novel metal nanoparticle. One phase synthesis, which is citron chemistry. Citron is used as reducing agent and stabilizing agent. And second one is two-phase synthesis or Schifrin method or Matthias-Brast method, which it is useful to put organic materials at the surface of nanoparticles, because some of organic materials, compounds, are not soluble in water. This is water-based synthesis. But this is two-phase, water and toluene. You put gold precursor in water. With the help of a phase transfer, you can transfer the ions, gold ions into the toluene. And here, this is the key point. Chemistry of gold and sulfur in the presence of a reducing agent. But our interest is these are groups. They can be everything. You can put anything you want. Just you need some synthetic hand to produce for you this molecule. Then with the help of this chemistry, you can put it here and go on. But the problem is, okay, here citrate, sodium citrate was as reducing agent because it provides electrons, and of course electrostatic repulsion stabilizing agent. But in this case, you have esteric hindrance. They are very long, attached to the surface, and they don't allow nanoparticles aggregate. That's why you can make them 1.5 nanometer stable in solution for a year. Okay, but the problem is here, sodium bromide plant. All of us always, when we are interested to use something, first of everything, we have to look at the bottom, the label. It's dangerous. So we don't prefer to use them. Recently, when I say recently, it means 10 years, more or less. There has been new and interesting synthesis, which is called bio-inspired synthesis, with the help of bacteria, fungus, and plant-mediated. First report in this research area was reported, actually the first work was reported with this professor from USA, published in Nano Letter 2002. And what was he did, simply he put some gold ion solution in soil which had some alpha-alpha plant. After few weeks, he took this leaf to TEM room, studied with TM, and he saw gold nanoparticles everywhere, in a stem, in leaves. So this means plant has reducing agent, and of course stabilizing agent, because there is no agglomeration. You see, single nanoparticle, stable, quite stable. So we got also interested in this field. There is one local plant in Iran. People actually are using this as a, how to say that? As a, no, it's not as like herbal. It's actually they're using oil industry, traditional oil industry, to give it